Oke. Apakah sudah terlihat? Oke, aman ya. Aku ternyata baru sadar kalau ternyata yang kemarin di-upload itu, ternyata yang ini masih banyak code yang rumpang ya, yang bawah. Kemarin kan sempat error gitu ya. Terus harus upgrade TensorFlow dataset-nya, dan ternyata di yang bagian bawah-bawah itu masih banyak code yang rumpang gitu. Kemarin kan sempat aku ubah nih. Nah, ternyata error lagi karena saat aku mau masukin syssplit, waktu kemarin aku share screen yang hari Senin, itu aku lupa masukin ini, jadi error gitu. Nah, terus sekarang udah aman semua kemarin. Aku kira cuman itu aja errornya, tapi ternyata di bawah-bawah itu kemarin kayak yang bagian image ini masih rumpang gitu ya. Ini juga masih rumpang. Jadi tadi aku isiin semua, aku coba buat diisi semua yang rumpang kemarin. Jadi nanti kita coba running ini lagi ya, karena kemarin juga masih belum bahas yang part ketiga gitu. Oke. Oke, baik. Selamat malam semuanya. Hari ini kita harusnya langsung ke yang kedua, device-based model in TF Lite 2, tapi karena kemarin kita ada yang belum dibahas di hari pertama, yang part ketiga, jadi kita bahas dulu yang part ketiga, gitu ya. Oke, kita mulai langsung aja, kita bahas yang part ketiga. Nah, part ketiga itu first primer on running model on mobile device. Oke, nah nih ya, running model itu ada pre-train model, ada pakai TensorFlow Hoop, not what you're looking for, ini build custom model kita. Kalau yang pre-train model udah pasti udah pada sering dengar gitu ya. TensorFlow Hub juga sempat kemarin kita bahas. Terus ini getting a basic model running. Ini aku juga kayaknya udah sempat kemarin Senin aku udah upload materinya termasuk yang part ketiga ini gitu ya. Nah ini contoh ya, build a model, create a simple model for Y sama dengan 2x-1 from simulated data and train it. Kemarin waktu kita jalanin codingan yang pertama, itu kita coba buat yang linear regression juga ya, itu yang contoh ini ya, kayak yang Y sama dengan 2x plus min 1 gitu. Terus export dan convert, generate the safe model and convert to TF Lite. Terus di verify, to perform evaluation on random data to verify the result. Terus yang terakhir deploy. Deploying the converted model on a mobile device, to Android atau iOS. Nah, tapi karena kita nggak bahas yang iOS, jadi kita cuma bahas yang Android. Terus yang ini transfer learning ya. Di kemarin harusnya kita bahas yang ini itu sampai ke akhir itu ada di transfer learning-nya gitu. Oke, kita running lagi dari awal aja ya yang ini. Jadi yang pertama kita train on model and convert it to TensorFlow. Ini ya, kita convert to TensorFlow. Kalau transfer learning, size of the data set, train from scratch, fine-tune on the layer, fine-tune only the lower layer, train the final classification layer to semakin kesana semakin similarity-nya datanya ya. Terus untuk transfer learning, feature extractor layer-nya itu input, conv 2D, max full 2D, conv 2D, max full 2D. Kayak biasa ini fitur ekstraktornya, terus train only in the final layer, terus dapat output. Nah, ini ya, converting a model to TF Lite. Yang ini, kita running. Kemarin aku sempat masukin yang ini, pip install upgrade si TensorFlow dataset-nya. Terus kita import TensorFlow dataset juga. Habis itu helper library-nya ada NumPy, Matplotlib, Padlib. Di sini pakai TensorFlow version 2.8, terus GPU device-nya udah ditemukan ya. Terus kita download version minis dataset. Di sini kemarin kan weight-nya 80, 10, 10, jadi 80% untuk train, 10 untuk validation, 10 lagi untuk tes. Nah, kemarin diubah jadi langsung split sama dengan train dari awal sampai 80%, terus train yang kedua itu 80 sampai 90%, terus train yang ketiga itu 90% sampai habis gitu ya. Oke, terus kita lihat class name. Oke, ini ada t-shirt top, trouser, pullover, dress, coat, sandal, shirt, sneaker, bag, ankle boot. Terus with open label.text, kita create label.txt-nya. Nah, di sini image size-nya 28 pixel, 28 by 28 pixel. Terus kita processing datanya. Di sini itu exercise-nya suruh kita tulis function buat normalize image-nya gitu ya. Nah, kemarin kalau codingan yang kemarin aku bagiin tuh di sini rumpang, jadi image terus code here gitu. Nah, di sini cast image to float 32, jadi tf.cast x image the type, kita ke float 32 gitu. Terus normalize the image in the range 0 sama 1 gitu ya, 0,1. Image dikali 1 dibagi 255,0. Terus dia akan nge-return image label gitu. Terus specify the batch size-nya 256. Kita create dataset-nya, kita bikin train batch, habis itu validation batch sama test batch. Oke, ini udah ambil yang batch size yang tadi, format example, prefetch 1, gitu. Terus ini building the model. Di sini tugas kita itu disuruh bikin build dan compile the model yang menampilkan ini ya, kayak yang ada di previous cell ini, yang kayak di atas ini, disuruh menampilkan seperti ini. Nah, di sini pakai model TensorFlow era sekuensial. Terus di sini kita disuruh set input shape-nya 28281, kernel size-nya 3, filter 16, use ReLU activation. Jadi filter 16, kernel size-nya 3, activation-nya ReLU, input shape-nya 28281. Jadi kalau yang dilihat tadi, habis conv 2D itu max pooling 2D, max pool 2D, terus lanjut conv 2D lagi. Oke, ini kita disuruh set number filternya 32, kernel size 3, user ReLU activation. Di filter 32, kernel size 3, activation-nya ReLU. Oke, terus ini flatten the output layer itu 1 dimension, terus kita add fully connected layer, 64 hidden unit, dan ReLU activation. Jadi dense unitnya 64, kayak yang di atas minta 64, activation-nya relu. Terus yang terakhir attach final softmax classification head. Di sini kita bikin TF keras layer dense unit 10. Activation-nya softmax. Terus kita set the appropriate loss function and use accuracy as your matrix. Di sini kita optimizer-nya Adam. Terus loss-nya sparse categorical cross entropy. Matrix-nya akurasi. Running history sama dengan model fit. Train batch. Epoch-nya 10. Validation datanya pakai yang tadi. Si validation batch ini. Oke, terus kita export to TF Lite. You will now save the model to TF Lite. We should note that you will probably see some warning message when running the code below. This warning have to do with software updates and should not cause any error. Oke. Nah ini ya. Kita disuruh pakai TF Save Model API untuk nge-save model kita. Terus dengan save model format nih. Export directory, save model /1, save TF, save model, export directory, export dir. For TensorFlow assets were written to save model 1 asset. Terus kita diminta ini select mode of optimization. Mode-nya speed, if mode storage, optimization-nya bakal TF Lite optimized for size. Kalau speed itu optimized for latency. Kalau else itu yang optimize-nya default. Nah, tugas selanjutnya itu diminta buat pakai TF Lite converter save model API to initialize the converter. Terus converter sama dengan TF Lite, TF converter kita pakai yang from save model yang tadi, export dir. Terus converter optimization-nya kita pakai yang udah kita buat tadi, optimization. Terus habis itu invoke the converter to finally generate the TF Lite model. Ini ya, ada warningnya. Tapi tadi kita emang udah dikasih tahu ini ada warningnya, tapi nggak akan ini ya, nggak akan ada penyebabnya buat kita gitu ya, nggak apa-apa ada warningnya. Nah, di sini TF Lite model file path-lib-path-nya model.tflite itu ini bytes-nya 259.776 ini. Terus kita lanjut tes the model with TF Lite interpreter. Ini kita pertama load TF Lite model and allocate tensornya. Ini interpreter, TF Lite interpreters. Model kontennya pakai yang tadi TF Lite model. Yang atas ini. Terus habis itu interpreter allocate tensor. Input index. Input details null index. Output index pakai yang get output tiles. Terus prediction get the result for the randomly sample test image. Prediction ada array kosong buat prediction test label sama image. Nah, kita bikin for loop image, label in test batch tag 50. Interpreter set tensor input index, image. Interpreter info, terus di prediction append dapetin tensor output indexnya, habis itu kita tes labelnya. Itu label 0 test image dan sampai array image-nya gitu. Terus utilize function for plotting. Kita bikin fungsi def plot image, prediction array, true label image. Oke, ini prediction array, true label image sama dengan prediction array i, true label i, image i. plt.grid false. Ini image np squeeze image, plt_show image simap plt.cm.binary. Predict labelnya np arrange masks prediction array. If predicted label sama dengan true, dia bakalan warnanya hijau. Kalau enggak, berarti warnanya nanti merah gitu. Oke, terus kita coba bikin yang fungsi plot value array. Sini. Terus this plot predicted labelnya nanti di set colornya red, kalau yang true labelnya blue. Terus kita visualize the output, select index of the image, ini minimum index is 1 and max index value is 50. Kita ambil indeks 49 di sini. Nah, ini hijau ya. Tadi kalau dia true warnanya hijau. Kalau false warnanya red gitu ya. Terus tadi yang satu lagi kalau this true label set blue. Kita coba yang lain ya. Nah, ini merah kalau yang trace. 61% trace code. Kita coba. Ini sneakers hijau. Ya, blue di label yang nomor 7, berarti dia ikut label yang nomor 7 gitu. Terus bisa coba lagi 15 misal. Ini t-shirt dia ada di label 0, 92%, tapi dia kayak masih di sini yang sebelah-sebelahnya kayak ada di label nomor 2, nomor 3, sama 6, kayak ada kemiripan mungkin di label nomor 2, 3, sama 6 gitu. Kayak yang tadi yang waktu dress tadi dia hampir dia juga code gitu kan. Dia code tapi dia disebutnya dress. Nah, makanya dia ada kayak kemiripan di 2 langsung gitu ya, tapi kayak lebih besar di dress, jadi dia merah padahal aslinya dia code gitu. Oke, ini cuman yang bawah buat prepare test image. Oke, mungkin kayak gitu ya, yang materi yang pertama kemarin, lanjutan materi yang kemarin. Nanti aku share yang ini juga ya. Kayak yang kemarin aku masih share yang masih rumpang code-nya. Oke. Mungkin ada yang mau bertanya dulu sebelum kita lanjut ke materi hari kedua ini. Oke, kalau nggak ada, kita lanjut aja materi hari kedua tentang device-based model in TF Lite 2. agenda hari ini kita belajar running TF model in Android app, terus TF Lite on device. Oke, udah siap belum semuanya? Tapi untuk hari ini aku mungkin nggak akan running di Android app-nya langsung, karena aku udah nggak pakai Android Studio gitu ya. Jadi aku mungkin cuma nunjukin hasil code-nya aja lewat VS Code. Tapi nanti aku kasih code-nya kalau memang ada yang punya Android Studio bisa di running sendiri nantinya. Nah, kita akan bahas banyaknya lebih ke TensorFlow-nya gitu. Oke, kita lanjut. Oke, recap. Tadi kita udah masih sempat bahas materi yang pertama, jadi kita bisa skip recap-nya. Nah, di sini kita ini video tentang on-device object detection, train and deploy a custom TensorFlow Lite model. Jadi di yang modul yang pertama tadi ada kayak yang ini ya, build custom model. Kita coba lihat. Aku share sound dulu. Oke, setting.
Hi everyone, welcome back to the learning pathway about on-device object detection. Object detection is a computer vision task that detects what objects are in an image and where they are located. In this video, I'll show you how to train a custom object detection model and deploy it to a mobile app by using TensorFlow Lite. Earlier in this learning pathway, I show you how easy it is to add a pre-trained object detection model to your mobile app. Pre-trained models are usually trained on general datasets, so they can recognize general objects. For example, in this image, a general model can recognize that there's food in the image. However, in many cases, you may find that you need a model that can recognize specific objects, such as the tomatoes or cheese in this food image. That's when you will need to train and deploy a custom model. There are 3 steps to do so. First, collect your training images and label them. Second, train a custom model using TensorFlow Lite Model Maker. This is a Python library that allows you to train machine learning models in just a few lines of code. There's no machine learning expertise required. And finally, deploy the custom model to your mobile app using TensorFlow Lite Task Library. This is a library that allows integrating TensorFlow Lite machine learning models to mobile apps in just a few lines of code. The first step, collecting and labeling your training images, is probably the most tiring step of the whole process. You need to collect the training images that contain the objects that you want to detect. In general, the more images you collect, the better model you can train. However, you can start small with a few dozen images for each type of object that you want to detect. In each image, you will need to draw a bounding box around each object and label it. In this image, for example, I labeled 4 objects and indicated that all of them are tomatoes. There are many tools that you can use for data labeling. Label IMZs is a popular open source app for data labeling. If you don't have your favorite data labeling app yet, you can check it out. Or if you prefer a web-based tool, check out Make Sense, which is also an open source tool. To make it simple for you to learn how to train a custom object detection model, we already prepare a dataset that you can use right away. This dataset contains about 100 of salad images, and there are 5 different labels: baked goods, salad, cheese, seafood, and tomatoes. Here are some example images from the dataset. The dataset contains about 100 of images and a CSV file with the labels and the bounding boxes. Each row of the CSV files represents an object in an image. The first column is data type. Train means the object is used to train the model. Validate objects are used to decide when to stop training to avoid overfitting. Test objects are not used during the model training. They are used to measure how well the model can generalize and recognize objects that it has never seen before. The following URI is the path where the image locates. We store the training dataset on Google Cloud Storage, but you can also use files from your local machine. This is the label of the object. And this is where the object is located in the training image. We only need to specify the upper left corner and the lower right corner of the body box. Now let's start step 2, train a custom model using this dataset. We'll use Model Maker, which is a Python library that makes it very easy to train models for common machine learning tasks. Instead of having to write a lot of code to train a model, you can do it in just 4 lines with Model Maker. Now let's go to Colab. Google Colab is an online tool from Google that gives you free access to computing resources to train machine learning models. Make sure that you have enabled GPU because it will significantly speed up your model training. You start with installing Model Maker, and then import the necessary packages. Then you can proceed to train the model. You need to choose a model architecture. Model Maker supports FGenDet Lite, which is a family of state-of-the-art object detection models optimized for mobile devices. There are 5 model variants. On one side, the Lite 0 model is small, fast, but less accurate. And on the other side, the Lite 4 model is the most accurate one in the model family, but it's also bigger and slower. Here's a graph that compares the model size, inference speed, and model accuracy. You can run several experiments with different model architectures and choose the one that is most suitable for your use case. In this demo, we'll use the middle one, Lite 2. Next, let's load the dataset. This is the salad dataset that I showed to you earlier. It's on Google Cloud Storage, but you can also use a file on your local computer. Model Maker automatically splits the dataset into training, validation, and test dataset for you based on the value you have specified in the CSV file. Then you can start the model training. It will take about 30 minutes to complete. Then we use the test data to see how well the model performs with images that it has never seen before. In this case, it shows an average precision of 40% across the classes, which is quite good for a mobile object detector. Model Maker uses TensorFlow under the hood to train the model for you. So the next step is to export the model to the TensorFlow Lite format so that we can deploy it to a mobile app. And finally, you can test the TensorFlow Lite model accuracy using the same test dataset. The TensorFlow Lite model average precision is 37%, which is a bit lower than the original TensorFlow model. There are several reasons for this drop. One of them is that we use quantization to shrink the model size by 4 times as a trade-off of reduced accuracy. If you want to retain the accuracy at the expense of a larger model, you can also choose to turn off quantization when exporting the model. Okay, now you already have the custom model. Let's download it and add it to the mobile app. Go to the Files tab on the left sidebar of Colab. Right-click on the TensorFlow Lite file and choose Download. It will take a few seconds to download the TensorFlow Lite file to your local computer. The final step will be integrating this model into your mobile app. We'll use TensorFlow Lite Task Library, which allows you to integrate TensorFlow Lite models into your mobile app in just a few lines of code. If you have used TensorFlow Lite before the Task Library release, you probably had to write a lot of code to integrate a TensorFlow Lite model into a mobile app. However, with the Task Library, this turns into just 3 lines of code. Let's switch to Android Studio to integrate the model into your mobile app. Adding a TensorFlow Lite object detection model to a mobile app is very similar to adding the MLKit API that I have seen earlier in this learning pathway. The only difference is that it would use TensorFlow Lite Task Library instead of MLKit for this integration. You'll find that many of the steps I will show you now to be very similar to the MLKit video. You can find a link to download the starter app from GitHub in the code lab following this video. The starter app already has some UI boilerplate code. You can select one of the preset images, and it will show up in the larger view. Or you can also take a photo with your phone camera. Let's start by adding the object detection model that you have trained earlier to the app asset folder. Please name it model.tflite. Then add the TensorFlow Lite task library to the app dependency. Go to the build.gradle file and add this line. Then next, go to the main activity and fire this method. The starter app is implemented so that whenever you pick an image, either by taking a photo using the camera app or selecting one of the preset images, this method will be called. Let's add the object detection code to this method. There are only 3 steps to use TensorFlow Lite task library. First, you need to create a tensor image from the image that the user has selected. Next, you need to create an object detector. Here you can specify a few options. You can make the model detect maximum 5 objects in the image. It will only keep the objects that have the highest confidence score. You can also set the score threshold so that the model will discard all detection results that have less than 50% confidence. And here how you specify the model that you copied to the app earlier. Then we feed the input image to the detector and print the detection result to logcat. Let's take a closer look at the code that prints the detection result. You can see that the object detection API returns a list of detection, each representing an object that it found in the input image. In each detected object, there's a bounding box or rectangle showing where the object is located in the input image. Let's run the app and see the detection result in logcat. You can see that the model can detect cheese and tomatoes in the image. Next, let's visualize the detection results by drawing them on top of the input image. The starter app already has a convenient visualization method. You can call draw detection result with a list of bounding boxes and text. Then you will see them show up on top of the input image. Then it will get back the image like this. Next, let's replace our logcat print with this visualization method. This chunk of code loops through the detected object list, extract the top label of each object, its confidence score, together with its bounding box, and creates a data object for visualization. Then we call the draw detection result method to draw them on the original image. And finally, we show the image on the screen. Now, you can rerun the app and see the visualization of the detection results. One important thing that you need to keep in mind is that TensorFlow Lite models run synchronously in the same thread with its caller. Because the model can take quite some time to run, we need to run the TensorFlow Lite code on a dedicated background thread to avoid blocking the app UI. You can see that we call the run object detection method, which contains the TensorFlow Lite code, using the default dispatcher to run it on a background thread. So that's all the steps needed to train and integrate a custom TensorFlow Lite model into a mobile app. You can go to the code lab following this video in this learning pathway to download the source code and go through the steps I have just shown you. I hope that you found this video and the learning pathway useful. Thank you for watching.
Oke. Jadi dijelasin ya, mulai dari train sampai nge-deploy custom modelnya. Oke, kita lanjut. Nah, part 4 itu Android Introduction. Ini installation and research. Itu download Android Studio, terus add dependency and add apt option. Oke, arsitektur of a model. Di sini ada arsitekturnya view, pre-process image, TensorFlow Lite classifier, sampai result. Terus initializing the interpreter. Di sini ada user touch here, terus image classify as a dog, gitu ya. Initializing the interpreter, steps involved in performing inference. Yang pertama mulai dari initialize the interpreter, itu model is loaded in the interpreter at this stage. Terus yang kedua, preparing the image input. Sini input image pixel buffer is converted to the format already recognized by the model. Terus yang ketiga itu perform inference. Sini pas input to the interpreter and invoke the interpreter. Yang terakhir, obtain and map result. To map our resulting confidence value to labels. Kalau dari teman-teman ada yang pernah pakai Android nggak ya? Android Studio. Ini mungkin kalau nanti ada yang mau download, mau coba terus download Android Studio, boleh banget ya. Oke, kita lanjut. Set the interpreters option. Di sini option a class for controlling runtime interpreter behavior. Terus ada set num thread, integer num thread. Terus set use NN API. Kemarin udah bahas juga NN API. Boolean use NN API. Set allow FP16 precision for FP32. Boolean allow. Terus add delegate, kemarin juga kita sempat bahas delegate, delegasi. Oke. Add and docs classifier. Oke, ini aku skip dulu, nanti kita demoin di akhir ya semuanya. Karena kalau ini aku nanti buka yang VS Code-nya gitu ya. Takut nggak kuat. Jadi nanti kita langsung di akhir bareng semua kita demoin. Oke, kita next. Part kelima, classifying camera image classification. Jadi di sini kita pakai machine learning buat identifikasi apa yang direpresentasikan oleh sebuah gambar. Terus kita quantize si MobileNet yang udah di-train dengan ImageNet dataset yang terdiri dari 1000 objek kelas yang berbeda. Ini juga ya, kamera image classification, demo. Oke, mungkin biar sekalian aja ya, dua ini kita demoin langsung, nggak apa-apa deh. Aku coba share screen buat yang itu. Oke. Kita di cat and dog. Nah, di sini cat and dog. Terus kita ambil yang app. Terus yang search main asset. Nah, kalau untuk yang asset ini converted model TF Lite-nya. Terus tadi yang di bagian Java ini classifier. Jadi di sini gimana cara kita nge-load modelnya, terus ini cuman ke arah masukin modelnya gitu ya, kalau di yang classifiernya ini. Nanti kalau dari yang model yang udah kita buat, di sini kita masukin ke Android-nya kayak gimana gitu. Ini kita pakai Kotlin ya untuk yang Android Studio-nya, Android-nya kita pakai Kotlin. Terus di sini ada view image classifier activity. Oke, di sini when user tap on click on view, ini result dari classifiernya yang tadi, image classifier yang tadi yang kita lihat yang dock gitu ya. Ada yang bagian bawahnya yang on click. Nah, itu. Terus kalau untuk rest ini yang isinya drawable V24, drawable ini sampai yang map ini itu kayak icon-icon yang kita pakai gitu. Di sini semua ada di rest. Terus image, icon-icon yang kita pakai. Kurang lebih untuk yang rest itu kayak ini ya, yang kita pakai icon-iconnya apa aja. Gitu. Kalau untuk yang ini di sini nanti import TensorFlow Lite interpreternya, terus ada class classifier. Ini ada data class recognition, dia buat tahu var id title string, terus title-nya, confidence float-nya. Nanti dia akan nge-return title, terus confidence. Jangan nge-return title sama confidence-nya gitu. Terus ya load model di sini, terus ada initializing the interpreter via method. Di sini ada load model. Di sini get the file description of the model, terus dia akan read model files channel-nya, terus dia akan nge-return model in map byte buffer. Ini ada private function, namanya ini load label list. Load label list, dia bakal nge-return asset manager, open label path-nya, terus dia buffer reader, use line it to list. Return the result after running the recognition with the help of interpreter on the past bitmap. Jadi ini udah yang ke bitmap-nya, recognizing image-nya, bitmap, terus dia convert bitmap-nya ke byte buffer, karena tadi kan yang di-read bentuknya ini ya, byte buffer format gitu. Jadi dia convert dulu bitmap ke byte buffer, ya, nanti yang dia return itu byte buffer-nya. Terus get short result, dia nge-sort result-nya. Priority queue-nya di priority queue, habis itu dia max result, comparator, classifier, recognition. Ini kita nggak bahas banyak kalau yang tentang Kotlin, karena kalau untuk machine learning cuma sampai dibikin ininya ya, modelnya gitu. Model machine learning-nya baru nanti bisa dipanggil sama Android itu kayak gini. Kalau untuk yang classifier activity ini cuma pas dia ngeklik gitu kayak on click. Itu untuk yang cat doc. Tadi terus kita lanjut ke yang image classification. Kurang lebih sama ini. Nah, yang beda di sini udah ada banyak ya. Kalau tadi kan cuman kayak classifier sama si image activity. Terus kalau di sini ada mulai dari kameranya, activity extension-nya buat gerak. This file illustrate Kotlin's extension function by extending the fragment activity. buat activity extension, terus ada auto fit texture view. Can be adjusted to a specified aspect ratio. Di kelas auto fit texture view, dia nggak auto fit. Ini set the aspect ratio for this view. The size of the view will be measured based on the ratio. Calculate from the parameters. Note that the actual size of the parameter don't matter. That is calling set aspect ratio 2,3 and set aspect ratio 4,6. Make the same result. Jadi ada paramnya 2, width sama height, terus buat relatif horizontal sama yang relatif vertical size. Ini cuma untuk tadi yang specify rasionya. Terus kamera to basic fragment. Handle several life cycle event on texture view. Oke, ini kamera fragment view on click listener. VT contact or reset permission result callback. Oke, ini tadi ada ID from the current camera device, ID kamera device-nya. Terus an auto fit texture view, pakai yang tadi auto fit texture view for kamera preview. Terus juga kamera capture session for kamera preview. Terus dia a preference to open kamera device. Kamera preview, terus ada kamera device.state callback yang akan dipanggil ketika kamera device change its state. Additional thread for running tasks that shouldn't block the UI. Terus ada handler yang buat running tasks in the background. Oke, ini capture request filter from the camera preview. Capture request generate by preview request filter. Ini untuk yang basic fragment ya. Terus ada yang tadi sempat dipanggil kamera activity. Nah, ini kamera activity yang tadi dipanggil di kamera basic itu untuk app compactivity. Dia tadi dipanggil di bagian yang atas. Terus ada compare size by area, compare to size based on their area di sini. We case here to ensure the multiplication won't overflow. Ada lagi confirmation dialog di sini, show OK or cancel confirmation. Jadi buat nampilin OK atau cancel konfirmasinya. Kamera permission. Jadi tadi kalau mau nyalain kamera ada permissionnya. Nah di sini ada OK atau cancel gitu yang dia akan tampilin. Terus constant di sini untuk image classification sample.camera. Request kamera permissionnya 1, baru nanti dia pick file name-nya. Jadi ada di sini juga request kameranya nanti kayak emang dia 1 atau 0 mungkin ya nanti. Kalau dia 1, kalau dia panggil si konstannya ini, request kameranya 1. Terus yang error dialog itu buat nampilin error message. Nah, baru di TF Lite. Nah, TF Lite ini yang bagian masukin si model kita ya. Nih, kita set interpreter, ini data class recognition-nya, kita set interpreter option-nya, terus loading model and label file into the interpreter, jadi kita masukinnya di sini load modelnya. Ini buat get description on the model, read the model files channel, terus return model. Terus ada private fund load label list di sini. Ada lagi yang recognize image buat resize image. Terus dia convert scale bitmap ke byte buffer kayak yang tadi juga ada yang di cat sama versus stock tadi juga dari bitmap diubah ke byte buffer biar bisa dibaca gitu ya. Terus ini write image data into byte buffer. Terus ini ada prepare the input for model. Ke model machine learning-nya tuh dimasukinnya tuh nanti di sini. TF Lite nih. Nih, kan udah kita sempat masukin ya mobile net-nya. Label mobile juga udah ada. Kita util, image utils Java. Ini image utils, this value is 2/16 kurangi 1 and is used to lamp the RGB value before their range are normalized to 8 bit ya. Sebelum normalize, dia udah dinormalize ke 8 bit gitu. Terus nanti final integer max channel value-nya ini, max channel value-nya sini kita bikin utility method to compute the allocate size in bytes of UV4 to 20 SP image of the given dimension. Ini ada buat yang dapat byte size yang tadi dari image ini. Terus save bitmap object for analysis, kita save di sini bitmap-nya. Oke, terus convert ke RGB ini ke A2. Ini kita convert tadi ke RGB. Turn transformation matrix from one reference frame into another. Handle cropping if maintaining aspect ratio is desired. And rotation. Ini ada parangnya, ada semua penjelasannya. Oke, kalau untuk rest sama kayak yang tadi ya, ini buat icon-icon kita gitu. Gambar, image, icon-icon yang kita masukin, nah itu ada semua di rest ini. Oke, itu ya untuk yang image classification. Kalau tadi yang image classification ini udah ada yang kayak kameranya gitu ya. Udah ada sendiri kameranya, semua udah ada permission buat kameranya gitu juga ya. Kalau yang waktu cat and dog kan cuman kayak classifier-nya aja gitu ya, belum pakai yang kamera gitu. Kita lanjut ke materinya. Kita coba lihat yang custom ini. Train a custom object detection model using your data.
Hi everyone, welcome back to the Machine Learning for Raspberry Pi series. My name is Kang from the TensorFlow team, and today I'll show you how to train a custom object detection model and deploy it on a Raspberry Pi. In the first video of this series, I show you how easy it is to run object detection on Raspberry Pi using a pre-trained TensorFlow Lite model. Pre-trained models were usually trained on general datasets so that they can recognize general objects quite well, such as they can recognize a mouse or a keyboard. However, in many cases, you may need a model that can recognize specific objects, such as the Android figurines. That's where you need to train and deploy a custom model. These are 3 steps that you need to do. First, collect your training images and label them. Second, train a custom model using TensorFlow Lite Model Maker. This is a Python library that allows you to train machine learning model in just a few lines of code, and there's no machine learning expertise required. Then finally, deploy the custom model to your Raspberry Pi. Actually, what you need to do is just to replace the pre-trained model that we used in the first video with a custom model that you're going to train now. The first step, collecting and labeling your training images, is probably the most time-consuming step, but also the most important one of the whole process. You need to collect the training images that contain the objects you want to detect. In each image, you will need to draw a bounding box around each object and label it. In this image, for example, I label 2 objects, an Android and an Android pig. There are many tools that you can use for data labeling. Label IMG is a popular open source app for this purpose, and let me show you how you can create an Android figurine object detection dataset by using Label IMG. I started with taking about 70 images of the 2 Android figurines that I have. In general, the more images that you collect, the better models that you can train. However, because we use a technique called transfer learning to train the model, you can start small with a few dozen images for each type of object that you want to detect. If you want to learn more about transfer learning, check out the link in the video description. Then I start Label IMG. Select the folder with the images. Then I go through each of the image and annotate the objects that I want to detect. So for example, in this image, I will create a bounding box for the Android and the Android pig. Then I go one by one through the images that I have taken and annotate the Android figurines in those images. You can download the Android figurine dataset that I have already annotated and use it so that you don't have to do the data labeling by yourself. My dataset is a zip file with 2 folders inside. The train folder contains about 60 images that we'll use to train the model. The validate folder contains about 10 images taken on different scenes, and we will use those validation images to test if our object detection model can generalize well on new images that it has never seen before. Now let's start step 2, train a custom model using this dataset. We'll use Model Maker, which is a Python library that makes it very easy to train models for common machine learning tasks. Instead of having to write a lot of code to train a object detection model, you can do it in just 4 lines of code by using TensorFlow Lite Model Maker. Now on your Raspberry Pi, please go to Google Colab. This is an online tool from Google that gives you free access to computing resources to train machine learning models. You can find the link to this Colab notebook in the video description. Colab requires you to sign in to run the notebooks. If you have any issues with Google Sign-in, make sure to turn off Chromium Sign-in and try again. Go to Settings, then type Sign. And make sure to disable Allow Chrome Sign. After sign, you should see your profile picture show up here. And next, please make sure to enable GPU because it will significantly speed up your model training. Go to Runtime, change runtime type, and make sure that GPU is enabled. Click Connect to start an instance. Now you start with installing Model Maker. And then import the necessary packages. Next, let's download the dataset. This is the Android figurine dataset that I have shown to you earlier. Here, I download a zip file from Google Cloud Storage and extract it to the Colab computer. You can also upload your training images from your local computer or Google Drive to Colab. Now we can start training our Android figurine detection model. We load the training dataset and the validation dataset from each folder. Then we choose a model architecture. Model Maker supports FGenDet Lite, which is a family of state-of-the-art object detection models optimized for edge devices. I'll talk more about different object detection model architectures in the next video. And now let's use FGenDet Lite 0, which is the smallest one in the model family. Okay, now you can start the model training. It will take a few minutes to complete. Okay, now the training has completed. You can see that here I set epochs equal 20s, which means that we'll go through the training dataset 20 times. You can look at the validation loss during training and stop when you see validation loss, stop decreasing to avoid overfitting. Then we use the validation dataset to see how well the model performs with images that it has never seen before. In this case, it shows an average precision of about 78% across the classes, which is quite good for an object detection model that runs on edge devices. If you are new to machine learning or want to learn more about what average precision means, check out the link in the video description. Model Maker uses TensorFlow under the hood to train the model for you. So the next step would be to export the model to the TensorFlow Lite format so that we can deploy it to the Raspberry Pi. And finally, you can test the TensorFlow Lite model accuracy using the same test dataset. The TensorFlow Lite model average precision is about 77%, which is slightly lower than the original TensorFlow model. There are several reasons for this drop. One of them is that we use quantization to shrink the model size by 4 times and improve inference speed at the trade-off of reduced accuracy. If you want to retain the accuracy at the expense of a larger and slower model, you can also choose to turn off quantization when exporting the model. Okay, now you already have the custom model. Let's download it to your Raspberry Pi. Go to the Files tab on the left sidebar of Colab and right-click on the Android.tfly model, then select Download. The next step is to run the model using the same object detection sample app that you used in the first video. You can also find the link to download the source code again in the video description. Let's reactivate the TFly virtual environment that we created in the first video. Run source TFly int activate. Okay, now go to the examples, Lite, examples, object detection, and Raspberry Pi folder. This is a folder containing the object detection Raspberry Pi sample app. And we will copy the Android.tfly model that we downloaded from Colab here. Okay, now let's rerun the object detection app with the default model. Run python detect.py. The default model is an object detection model trained on a general dataset that was downloaded from TensorFlow Hub. So that's why it can detect there's a clock in the image, which is a general object, but it made incorrect detections about the Android figurines. Now let's run the detection script again, this time specifying that we want to use the android.tfly model that we just downloaded. Python detect.py and set the model parameter to be android.tfly. Now you can see that the model can detect the Android figurines that it was trained on. Because we retrained the model to recognize the Android figurines, the model has forgotten everything about the classes that it was trained on before. So it no longer can recognize the general classes like the clock in the image. Now it can only recognize the Android figurines. So that's all you need to train a custom object detection model and deploy it on your Raspberry Pi. In this video, we use the FGenDet Lite 1 model architecture, but there are other model architectures that you can choose from. Whether if you want a model that is more accurate or a model that runs faster. We'll talk more about different object detection model architectures in the next video, and I will also give you some advices on which model architecture that you should choose for your use case. If you're new to training machine learning models, it's also important to familiarize yourself with the concepts in responsible AI. You can learn more about those concepts in the link in the video description. Thank you for watching and see you in the next video.
Oke, ini tadi dijelasin yang sampai ke Raspberry Pi juga ya, yang buat deploy di Raspberry Pi. Oke, kita lanjut. Sebelum lanjut, mungkin ada yang mau tanya sampai di sini. Ada yang mau bertanya? Oke, kita lanjut mungkin. Oke, ini Introduction to Object Detection on Raspberry Pi.
Hi everyone, my name is Kai and I'm a developer advocate in the TensorFlow team. Welcome to Machine Learning for Raspberry Pi, where I'll show you how to make your Raspberry Pi smarter with AI. Hi everyone, my name is Kai and I'm a developer advocate in the TensorFlow team. Welcome to Machine Learning for Raspberry Pi, where I'll show you how to make your Raspberry Pi smarter with AI and machine learning. In this video series, we'll talk about how to do object detection on Raspberry Pi. Here are what you will learn. First, I'll show you how to download a pre-trained TensorFlow Lite object detection model and deploy it to your Raspberry Pi. This model can recognize general objects such as an apple, a television, or a car. Second, we'll learn how to train a custom object detection model to recognize specific objects in your problem domain, like recognizing different Android figures. Third, I'll talk about which object detection model architecture you should use in your use case, depending on whether speed or accuracy is more important to you. And lastly, you learned how to speed up your model inference by using Google Coral Edge TPU. Each topic will be covered in one video. In this video, we'll talk about the first topic, using an off-the-shelf model to run object detection on Raspberry Pi in just 5 minutes. Now, let's get started. The easiest way to start running object detection on Raspberry Pi is to download a pre-trained TensorFlow Lite model and deploy it on your device. For those who don't know, TensorFlow Lite is a library to run TensorFlow machine learning models on edge devices such as Raspberry Pis, smartphones, or even web browsers. Before we download the model and run the code, please make sure that you have the latest version of Raspberry Pi OS because you will need to use a camera driver that is only available on the recent versions of the OS. You can check your OS version by opening terminal on your Raspberry Pi and type this command. You can find all commands in this video in a gist in the video description. So in this video, I use a Raspberry Pi 4 running Raspberry Pi OS version 10, as you can see from here. If you have an old version of the Raspberry Pi OS, you can go to the Raspberry Pi website, download the Raspberry Pi imager, and flash the latest version of Raspberry Pi OS onto your SD card. The website URL is in the video description. You need to connect a camera to your Raspberry Pi to run the sample. You can either use the Raspberry Pi camera module, or you can also use a USB camera and connect it to the USB port in your Raspberry Pi. If you use a Raspberry Pi camera module, make sure that you have enabled it in the Pi OS setting. Go to the Raspberry Pi menu, select Preference, then Raspberry Pi Configuration. Go to Interface and make sure to enable the camera. You will need to reboot the computer before this change takes effect. After reboot, open terminal. I'm going to run a series of commands to set up the Raspberry Pi. We start by running this command to update the local packages. Okay, then next, check your Python version. Make sure that you have Python 3.7 or newer to proceed. Then we'll create a Python virtual environment to make sure that the Python packages that we're going to install won't have any conflict with other packages that you already have in your system. This step is optional, but is highly recommended. Start installing virtual environment via the pip command. Then create a virtual environment called TF-Lite. Then let's activate it. Now let's clone the TensorFlow examples repository, which contains the Raspberry Pi object detection sample code that you are going to use. Then change directory to examples, Lite, examples, object detection, and Raspberry Pi. This directory contains the source code that we are going to run for object detection. Run shell setup.sh to install the TensorFlow Lite package and other Python dependencies required by the sample. Then finally run python detect.py and see what the model can detect. Because this object detection model was trained on a general dataset, it can recognize general objects like a keyboard, or a clock on the wall, a cell phone, or a water bottle. But if you need to detect specific objects like different kinds of Android figurines, you will need to collect training data and train a custom object detection model. I'll show you how to do it in the next video in this series. The model runs at about 2 frames per second on my Raspberry Pi 4. If you want to make it faster, check out another video later in this series to learn how to use the Coral Edge TPU to speed up the model inference. So that's all you need to run object detection on Raspberry Pi. Now let's take a closer look at the code that users ran. In the setup shell script, we do 2 things. The first thing is that we install the Python dependencies that is required to run the sample. One of them is the TensorFlow Lite runtime pif package. It contains the minimum runtime to run TensorFlow Lite models, and it is way smaller and much faster to install compared to the full TensorFlow package. Then we download a pre-trained TensorFlow Lite models from TensorFlow Hub. For those who don't know, TensorFlow Hub is a repository for TensorFlow pre-trained models, just like how GitHub is for open source software. You can find many models from Google and other contributors on TensorFlow Hub. There are many TensorFlow Lite object detection models on TensorFlow Hub that you can choose from. Here we use a model called Lite. It is a state-of-the-art object detection model for edge devices at this time the video was created. In another video later in this series, I will explain more about how to choose a model for your use case, whether inference speed or accuracy is more important to you. And now let's take a closer look at the detect Python script that runs the object detection model. We start with setting up OpenCV to capture the images from the camera. Then we initialize a TensorFlow Lite object detector. It specifies the TensorFlow Lite model and some optional configurations, such as the confidence score threshold to detect an object, etc. You can take a closer look at the available options in the code. There's no need to specify a label file to map the class index to a human-readable label because TensorFlow Lite model we use in this sample already includes the label file inside. Then we start the loop to continue capturing the frames from the camera until you press the escape key. And here's the main code that runs the object detection. So we start with capturing the frames continuously from the camera and just like mirror it so that it looks more natural. Then we feed the frames to the object detector's instance that we created earlier. This function returns a list of detected objects with its class name, score, and bounding boxes. You can change the object detector option when initializing the object detector so that it will only detect certain types of objects, such as only detecting keyboards from the images, or taking only objects that were detected with a confidence score above a certain threshold. And finally, we call a utility function to visualize the detection results on the screen. So that's all you need to run object detection on Raspberry Pi. Very easy, isn't it? In the next video, I'll show you how to train a custom object detection model to detect specific objects that you care about. You'll learn how to collect and label your training data, then using TensorFlow Lite Model Maker to train the custom model. Thank you for watching and see you again.
Oke, itu tadi ya caranya buat yang udah kita sampai running di Raspberry Pi gitu ya. Tadi di akhir ditanya gampang kan gitu. Oke, ini aku kasih link yang tadi dia sempat sebutin gitu ya, kalau mau download. Oke, kita lanjut materinya. Oke, kita lanjut part yang ke-6. Object Detection App. Oke, di sini ada Object Detection Model. Itu ada yang pertama, identifies class of object along with localizing them. Terus yang kedua, mobile net SSD train on Jojo dataset. Common object and context ya. Terus Jojo dataset has 80 class, tiapnya 80 class. Label file is used to list Coco dataset, Coco class, and map to output confidence. Kita coba demonya. Aku pindah dulu ke yang tadi ya. Oke. Object detection. Oke, yang pertama kita initialize the parameter itu ada di classifier Kotlin ini KT. Ini kita cuma kalau yang untuk machine learning itu semua dimasukin di sini di TF Lite ini. Jadi kita yang pertama tadi interpreternya initialize interpreter. Interface, interactive different recognition engine, interface classifier. Immutable result returned by classifier describing what was recognized. Ada class recognition. Sini unique identifier for what has been recognized, specific to the class, not the instance of the object. Ada file ID, display name for the recognition, file title, assertable score for how good the recognition is relative to others. Higher should be better. Terus ada yang confidence. Optional location with the search image for the location of the recognized object. We get the location, set location, terus to string, kita override to string. Sini kita have object detection API model. Kita bikin modelnya di sini. Config value, pre-allocate buffer, terus output location, array of shape, bit size, num detection for, contains the location of detect box. Sini ada output location-nya, output class, array shape, bit size, num detection, contain the class of the type box. Terus juga class, output class, jadi output location ada output class, output score, num detection. Terus ini buat recognize image yang tadi bitmap. Override buat set num thread sama set use NNIPI. Sini kita buat asset manager, model file name, label file name-nya, initial input size-nya, this quantity size itu boolean, true atau false, terus specifier, file tf lite object detection mode, API model. Di sini untuk kita bikin si API modelnya. Oke, kalau untuk yang kayak custom view, environment, terus tracking ini pakai kamera ini sama kayak yang tadi ya, yang ada di image classification itu juga pakai kamera. Tapi kalau untuk yang di object detection ini ada environment-nya juga buat image utils, logger, vertex. Ada custom view-nya tadi juga ada kalau yang di sebelumnya. Tadi juga ada auto fit texture view-nya. Core view-nya, dari result view-nya. Ini kalau tracking pakai kamera yang tadi. Legacy kamera fragment, vector activity. Untuk res-nya sama, res-nya cuma buat input-inputnya. Oke. Harusnya di minggu ini kita tuh sampai ke iOS, tapi kayaknya berat banget kalau sampai ke iOS. Jadi kita cuma sampai Android-nya aja. Terus tadi juga beberapa ada Raspberry Pi. Ini untuk yang TF Lite, runtime interpreter, import interpreter. Ini untuk rock paper scissors. Fast for learning, object detection. Kalau dari teman-teman mau di-share semua nggak nih yang buat Android-nya? Aku share semua filenya gitu yang buat Android. Kalau untuk iOS mungkin juga mau nggak ya? Kalau iOS-nya, tapi kita kan nggak jelasin iOS gitu ya. Cuma mungkin kalau ada yang tertarik tentang iOS gitu. Ya, siapa tahu bisa buat belajar. Soalnya sama aja gitu, tetap cat versus dog, image classification sama object detection, tapi cuman itu di iOS. Ya, aku share ya yang buat di iOS juga. Ya, nanti aku share di Classroom. Kalau pakai Flutter gimana? Aku tuh nggak pernah coba pakai Flutter gitu ya. Mungkin bisa dieksplor kayak ini kan yang sekarang juga kayak Android-nya juga Kotlin gitu ya. Karena selama ini kalau ngerjain project kan juga pasti yang machine learning itu pegang hanya machine learning-nya, terus kita cuma tahu di bagian mana si machine learning-nya itu dipakai. Jadi selama ini kalau kita naruh machine learning di Android itu cuma ditaruh di bagian yang tadi TF Lite. Nah, ini modelnya, buat ke modelnya itu kayak gimana itu nanti itu urusan machine learning-nya gitu. Tapi selebihnya ke Android-nya itu sampai icon-iconnya yang dipakai apa aja, itu udah bukan kerjaan yang untuk machine learning-nya, tapi itu udah buat yang Android developer-nya gitu. bikin kayak gitu. Kalau untuk yang machine learning itu biasa cuma sampai ditaruh F-Lite-nya, ini kita kasih modelnya kayak yang tadi ini. Nah nih ya, model TTF-Lite yang udah kita convert dari codingan yang udah kita bikin. Nah itu modelnya baru kita kasih modelnya. Terus modelnya itu biasa dipanggil TTF-Lite yang classifier ini. Semuanya sama, ada TF-Lite-nya itu kan classifier. Bahkan kadang buat beberapa machine learning itu cuma sampai kita bikin si modelnya aja. Sampai kita bikin model yang ini, yang atas, yang ada di aset itu model .tf-lite. Lebih kayak gitu. Ini juga ada yang model. Jadi kita yang machine learning nggak mungkin kok sampai bikin sampai Android-nya gini. Jadi ini cuma contoh aja kalau yang Android kayak gini. Tapi kita kalau bikin sih cuma sampai modelnya gitu. Nggak mungkin kita dikasih semua sampai selesai. Kecuali kalau kita ambil yang kayak full stack ya. Oke. Aku pindah layar lagi. Nanti itu aku share semua aja ya, biar bisa belajar. Karena emang kalau dari kita yang para instruktur emang nggak kayak yang bisa Android-nya juga. Tuh. Dan besok kita udah nggak bahas tentang Android sih, jadi besok kita udah bahas mulai ke data pipeline. Hari Jumat kita udah nggak bahas tentang device-based model, jadi kita Jumat bahas untuk yang data pipeline. Oke, kita lanjut. Ini playlist. Oke, ini untuk setup machine learning-nya di Android. MLKit.
Selama gap year ini, aku banyak menggunakan Grammarly untuk menulis pemuda.
Hi, welcome to Machine Learning app on Android using MLKit. I'm your author, Yusuf Saber. A little bit about me before we get started. I've worked over the past 5 years as a professional Android engineer, and I've worked at many startups as well as mid-sized and large companies. Currently, I work for a company called Vocera Communications as a senior Android applications engineer. The apps that I've worked on have been downloaded over 50 million times and growing in total. And I currently hold a master's degree in software engineering from Ryerson University in Toronto, Canada. Now for the course overview. What we'll learn in this course is, of course, how to use MLKit on Android. We'll start with that in section 1 with what is MLKit. From there, we'll look at setting up the app so that we can start adding our MLKit modules. In section 3, we'll look at the first module, text recognition. From there, we'll move to Section 4, Face Detection. After that, we'll look at Section 5, Barcode Scanning, where we'll look at scanning different types of barcodes, including the regular one and QR codes. In Section 6, we'll look at image labeling, and we'll look at the local model as well as the cloud-based model. And finally, in Section 7, we'll look at landmark recognition, so we can try to pick up things like the Eiffel Tower, the CN Tower, Niagara Falls, the pyramids in Egypt, and all sorts of other landmarks. Some of the prerequisites for this course. This is of course an Android course, and of course we're not using Eclipse anymore, so you do need some experience with Android Studio. And of course, you should know your way around Android development. And you don't need any prior knowledge of machine learning. If you do know a little bit or a lot about machine learning, that's great. It'll definitely help you with the course, but you don't need to know the ins and outs of machine learning in order to use MLKit. Now, some things to get excited about when working with MLKit. The first thing is that MLKit is very easy to set up, as you'll see in the beginning videos of this course. The second thing is that MLKit is very powerful. If you try to do some of the things that MLKit does without using the MLKit library, you would be writing code for years. And finally, MLKit is improving every day. So the 5 models that we talked about in the what we'll learn in this course section, so the 5 models that we're going to talk about in this course are just the beginning. The MLKit team is already working on Smart Text, which is a text completion module. And after that, month by month, year by year, they'll be releasing more and more models for us to work with in MLKit.
Anvil is a platform for building full-stack web apps with nothing but Python. Anvil lets you build your app's front end by
Hi, welcome to Setting Up the App. In this section, we're going to discuss camera setup, UI setup, and preparing to use MLKit. Camera setup. In this video, we're going to discuss Google's sample MLKit app, the camera implementation, and the graphic overlay implementation. If we open up Android Studio and we open the application that's available to download with the course, we're going to open up this class Live Preview Activity. Now, just so you know, this is Android's MLKit sample app. So one thing that I did change from the base download is that I changed the default launcher activity from chooser activity, and I made it live preview activity. Essentially what chooser activity does, if we click into it, it gives you the option to either, as you can see here, the descriptions, vision detectors demo with live camera preview, which is what we're going to look at. And the other option is vision detectors demo with a still image. So we won't be looking at this one for this course, but if you want to, you can go into it and take a look. So our app will default to live preview activity as the default launcher activity. Now for this video, we're just going to take a quick breeze into the code and see what exactly it's trying to do. There are 3 main classes that we'll be looking at: camera source preview, and graphic overlay. And we'll come to learn what these do. Now the first thing we'll look at here is our onCreate class. This is all standard, your set content view. Let's look at the XML for that real quick. So you'll see here, the preview doesn't really show too much, but just so you can see, it's all wrapped in a relative layout. And the first child is a camera source preview. So what the camera source preview is, it's basically a window, which is this gray area, which allows a camera feed to be displayed on your screen. You'll see that it has a child that's a graphic overlay, and that basically allows us to take the coordinates of the camera and to draw something over it. So for example, if I want to draw something here, I can get that from the camera feed and I can say draw a square here or draw a circle here, for example. After that, here you have the bottom stuff over here. The text here is just some display. like a title, for example. And then the bottle, you have your controls. The spinner here, the toggle button is for switching the front camera and the back camera. And then the spinner here, as you'll see when we demo the app, is for switching the different detector types, such as label detection or face detection. Okay, so going back to live preview activity. We'll see here that we then create an instance of the camera source preview and the graphic overlay. We get them from the XML so that we have a preview and a graphic overlay. And then we simply set up the spinner and we set up the toggle button. Nothing fancy there. And then finally, since we're running on a later version of Android, we have to check that we have our permissions. And if we don't, obviously we get them, asking the user for them. And then we have your on request permission results, so that once the user selects yes, okay, I give you the permission, we can go back here and create the camera source. Now create camera source here, as you can see, it takes in a model, a string, which is called model. And basically it checks which string we passed in, whether it's classification, text detection, face detection, barcode detection, or image label detection. And then it switches the machine learning frame processor. We'll get more into that in the later videos. But basically we're telling the camera source, I want to detect barcodes here, and here I want to detect faces, and here I want to detect text. So that's essentially what this is doing here, and that's in the spinner widget on our main screen. And that's pretty much what live preview activity does. The rest of it is just some camera handling things. For example, in on resume, we start the camera source. Pretty basic camera stuff if you've ever dealt with the camera. And then on pause, we're stopping it, etc., etc. We're getting the permissions. So let's start looking at camera source. So camera source here, as we said, it's basically like a helper class that is used in this application to handle all the camera stuff. I don't know why, but they decided to use the old camera implementation. You'll see here, even it's crossed out, it says android.hardware.camera is deprecated, and we should actually be using camera 2. I don't know why they're not using it in the sample application, but you can use camera 2 in your own application if you desire. So camera source holds an instance of camera, and it also holds an instance of vision image processor. As we just discussed, vision image processor is basically, it's an interface that allows us to process ML detectors. So you'll see here, if we look at some of the implementations, we have barcode scanning processor, we have face detection processor, text recognition processor. So all of these implement vision image processor in their own way by implementing these 4 methods here. We'll get more into that in later videos. So essentially camera source, as you can see, it's a very, very large file. It has 732 lines. And basically, we don't need to get into the details of it. You just need to know that camera source handles the camera. Moving on, we're going to look at camera source preview. So camera source preview is sort of the feed that allows the camera feed to be shown. So here we have a camera source and a surface view. These are our 2 main components, as well as a graphic overlay. So the surface view is the UI widget that allows a camera feed to come through. The camera source is giving us the feed so that we can display it in the surface view. And then graphic overlay is just another layer of UI that's allowing us to display things on the camera feed. Again, we don't need to be boggled up in the implementations here. I just wanted to quickly go over it just so that we're aware of what's happening. So it's starting and stopping the camera source, on stop and things of that nature. Start if ready is checking a bunch of different things such as the permissions, etc. And then it's starting it. And yeah, the camera implementation is sort of beyond the scope of this course, but it is here. It is pretty straightforward stuff. You can Google, how to work with a surface view, for example, if you want to go over it. And that's pretty much camera source preview. And now looking at graphic overlay. So graphic overlay, it's basically another UI layer that allows us to draw things over the camera feed. So we'll see here that it gives you things like the preview width and the preview height, and then it does a bunch of different modifications such as translations and scales and things of that nature to get the image coordinates properly. And you can see here that it has on draw method, which takes a canvas. Obviously all views have this method, but this allows us to, this is the method that actually draws the stuff onto the camera feed. So I actually have an emulator here running the application, and I'm basically going to give a quick sample of it since we know what it does. So that's me. Hi. And as you can see, I have face detection on, and it's, although it is sideways, let me fix that. And as you can see, face detection is working. So it's detecting my right eye and my left eye, and the happiness level and the ID. So the ID is the face that it's looking at. Since I'm the only face on the screen, I'm getting ID 0. And this is a cool thing. It detects happiness as well. So when my face is just still, you see happiness goes to almost 0. But if I smile, it goes to 0.98. So it's almost at 1, detecting, hey, this guy's really happy. So if we click on face detection and we change it to text detection, for example, I have my copy of effective Java here, and you can see, if I can bring it on the screen, it picks out the words very clearly. The name, even Joshua Bloch, is there, all the words. If I bring it down, it'll pick up sun there from the source, Java. So the text detector picks up text. It's actually picking up some of the stuff on my board there as well. If we look at barcode detection, let's go back to effective Java, and if we show it our barcode, you'll see here it'll pick up the barcode perfectly. So this is cool. This can be used to do things like checking the prices of whatever barcode item you may have, for example. And if we look at label detection, so there's two things here, label detection and classification. Essentially the difference is label detection allows us to label things in the screen. So if I click on it, once it loads there, it's showing white. So I'm just going to put up my phone here, and you can see here that it's showing, you know, selfie, goggles, beard, glasses, cool, thinks I'm cool, a hand, mustache, nails. So it's just labeling things that it sees on the screen. And if I switch to classification, so now with classification, it's giving us a strength of what it thinks is the most prominent thing on the screen. So for example, here, if I put up, just so you have a black background, you'll see it shows sunglasses, beer glass, it thinks it's there, spatula, and it gives you that number. So that number is sort of the strength. If there's one clear thing in the image, it'll tell you, it'll have a higher number. So it'll be closer to 1, maybe 0.9, for example. And then you can say, you're looking at the Eiffel Tower, for example, or at a car. And then this button here just switches the camera from the front to the back. My emulator doesn't have multiple cameras, so clicking it won't do anything. And that's essentially the application that we're going to be going through. As I mentioned, the main thing where the different detectors come in are the vision image processor. And this is where we'll spend the bulk of our time looking at these different implementations.
Baru bangun, kerjaan udah numpuk.
Hi, welcome to Text Recognition. In this section, we're going to discuss implementing text recognition on the device, implementing text recognition on the cloud, and trying out text recognition. Implementing text recognition on the device. In this video, we're going to discuss working with Firebase Vision Text Detector, detecting the camera feed image, and finally displaying the results on the screen. In Android Studio, if we open up our live preview activity, we discussed previously that when we want to switch the models, we basically need to feed in a different frame processor into the camera source, like this for example. So since now we're talking about text detection, we're going to look at this class here, text recognition processor. Now if we click into here, the first thing we'll notice about text recognition processor is it overrides a lot of methods. So we'll see that it extends vision processor base, and its generic type is Firebase Vision Text, which we'll get to a little bit later. But let's look at vision processor base. We'll notice that, as expected, it takes a generic type and that it implements vision image processor. So vision image processor, as we can see, is simply an interface. It has three methods overloaded called process and one called stop. The first thing we'll notice about these process methods is that they all take a graphic overlay as the last parameter, right? Here, here, and here. And the other difference is that this one takes a byte buffer and a frame metadata. This one takes a bitmap, and this one takes an image object and a rotation. Now these two are basically used to process still images, and this one is used to process a live camera feed. And this is the one we're going to discuss in this course. Now if we go back to vision processor base, we're actually going to take another step back and then come back into this. So we'll go back to text recognition processor, and we'll look at some of the methods that are being overridden here. We'll notice on failure and on succeed, which these are used, as we'll see, when the image reads texts and then spits back the data. This is where it'll be. And then detect an image and stop. And of course we have our constructor. So in our constructor, we'll notice that we are instantiating Firebase Vision Text Detector. Now Firebase Vision Text Detector is actually the class that does all the work. As you can see here, this is a private class in the sense that it is not open sourced. So we can see here that there's a bunch of different variable names, var1, zz, gw, etc., etc. We're not meant to know what goes on in here. And we'll see how detector gets the job done. So we'll look at detector here where it's used. Stop, this is pretty straightforward. We don't really need to discuss this. The two important methods here are detect an image and on success. So let's look at detect an image. So detect an image is a method that's overridden, and its return type is a task of generic type Firebase Vision Text, and the input parameter is a Firebase Vision image. Okay, so let's look at what this overrides. So this is an abstract class in Vision Processor Base, which again, text recognition processor extends Vision Processor Base. Let's look at Vision Processor Base. And the method we want to look at is this abstract method, detect an image. So let's just do a search and see where this is used. So we'll see that there's three matches. It's used in detect in vision image, and it's there in a comment, and then there's the abstract signature. Okay, so here's where it's used. Let's just clean this up a bit here so we can see what's going on. Okay, so this method, detect in vision image, takes a Firebase Vision image, a frame metadata, and a graphic overlay. Now basically it invokes detect in image with the image parameter, and then it adds an on success listener and an on failure listener. And as you can imagine, basically what this does is it'll invoke on success that is implemented here. And on failure, it'll invoke what's implemented here. Okay, so that's pretty straightforward. Now looking at detect in vision image, let's again do a search for this and see where it's used. So here we have 4 matches. There's the method signature here, and then we'll see that it's used in each of the process methods. So there's the first one with the camera feed, byte buffer, and frame metadata. And then there's the one with the bitmap, and of course the one with the image right here. So let's look at the one with the camera feed data, byte buffer, and the frame metadata. What does this method do? So this method, we'll see here, it creates a Firebase Vision Image Metadata object, which is basically like a settings object. We can ignore that for now. We can just leave it as it is, and we can use it as it is in our own app. And then basically it invokes detect in vision image. Now this process, if we go back to text recognition, we'll see that detect an image. Now we'll see here that this method process, if we right click on it and we go to find usages, and we say yes, we want to find usages of the base method, we'll see here that if we go to our camera source app, it processes it in the run method. So basically while the camera feed is running, we want to process the camera feed with the data of the camera, and our frame metadata is just some of the camera information, and then the graphic overlay that we defined in the live preview activity. So we'll see what it does here is it passes all of that information into detect in vision image, which again invokes detect in image, which is abstract, which we implemented here. So it's our detector.detect in image. So basically we're telling it, take the image from the camera feed and feed it into this Firebase Vision Text Detector. And as we can imagine, this Firebase Vision Text Detector, which again is not open source, it searches based on a local set of strings for any text that's in the camera feed. And then the results going through here, through this process, it'll return through this process here, and with the onSuccess listener, it'll give us back our information over here in onSuccess. Now, let's look at Firebase Vision Text. And keep in mind, Firebase Vision Text, this is the class that's used with Firebase Vision Text Detector in order to return the text. So in your own code, you don't need to use text recognition processor. You can implement your own code structure, but you will need to use Firebase Vision Text Detector and Firebase Vision Text. Now, in the onSuccess method, we'll see that it returns Firebase Vision Text. The other stuff we can ignore for now. Our goal is to get the text out. We want some strings. So looking at Firebase Vision Text, we'll see 3 for loops here within each other. The first thing we're doing is we're getting the blocks from the results. Okay, so if we open up Firebase Vision Text, we'll see that there are 3 main building blocks here. There's block, and each block contains, if we click into it, we'll see that it contains a list of lines, and each line contains a list of elements. And each element, you can't see it here, but it has a bunch of strings and some other stuff. So if we go back to our for loops here, we'll see that if we can get the blocks and we can iterate through them, we can get a list of lines. And if we iterate through them, we can get a list of elements. And if we iterate through the elements, we can get a list of the strings that we retrieved. So here, this is basically taking it and putting it onto the screen. But if you just want to get the string, what we can do is we can say string s equals elements.get k dot get text. And there you have it. We have the string. We have obviously a list because of all the loops. So we'll have a array or a list or what have you of strings that were discovered on the screen. And this graphic overlay, as we mentioned, it's just taking the text and drawing it into a rect and then onto the canvas, and it's just displaying it onto the screen. Pretty straightforward stuff. It's not stuff that is really important for this specific video. So now that we know that detect in vision image basically processes everything and does all that through detect in image, and all of our results are in on success, we can make some modifications here if we want to. So we can do something like, here we can get the text and we can put it into a log, or we can display the text in a different way, for example. We can do whatever we want in here and it's nice and clean. And that's basically how text recognition on the device works.
Anvil is a platform for building with nothing but Python.
Hi, welcome to face detection. In this section, we're going to discuss implementing face detection on the device, configuration of face detection, and trying out face detection. Implementing face detection on the device. In this video, we're going to discuss working with Firebase Vision Face Detector, detecting the camera feed image, and displaying the result on the screen. If we open up Android Studio, we'll remember here that in our main case switch code here, that this is where we can access all of our different processors. So since this time we're looking at face detection, we're going to want to open up face detection processor. So this has a similar structure to the text recognition and all the other processors that we looked at before, in that it extends vision process base. So vision process base, just to give a quick recap, has three process methods: one that takes an image, one that takes a bitmap, and one that takes a byte buffer and frame metadata. And then it also has a stop, on success, on failure, and detect in image methods. These three being abstract. Now we're interested in this one because this is the one that uses the camera feed. Now, going back to face detection processor, we see that the generic type that's used here is a list of Firebase Vision Face, and that's because it returns a list because here it could detect multiple faces in any given camera scene. So we'll look at Firebase Vision Face a little bit later. Now the first thing that we notice is that instead of just instantiating the detector here, we have some options, and we'll talk about that in the next video. But for now, we'll see that we have the Firebase Vision Face Detector, and we instantiate it just like the other ones by getting an instance of Firebase Vision and then invoking get Vision Face Detector, and this time with the options passed in. After that, we look at detect an image, and that gets invoked similarly to the text detection, where we just invoke detector.detect an image, and we pass in the Firebase Vision image. Finally, in onSuccess, here we can see that our return type, let me just clean this up a bit so that it's a little bit easier to read. Okay, so we see here that our first parameter is a list of Firebase Vision faces, and that's expected because that's what we pass in over here to our generic type in the class signature. Now, what we're going to do to get the faces is we're going to loop through each face, right? So we're going to loop through each face here, and we're just going to create a face graphic and then add that to the overlay. Now, looking at face graphic here, we see that it's simply, what we're doing here is we're writing text. So we're saying happiness level, right eye, left eye, and then the coordinates of it. And we're also giving a dot for all the different points that are shown here. So bottom mouth, left cheek, left ear, left mouth, left eye, nose base, right cheek, right ear, right eye, and right mouth. So we're basically taking the face that we detected and we're drawing dots or little circles where we find the coordinates of all of these different things. We'll look more deeply into this class in a later video because we do some customizations around here. And that pretty much summarizes the Firebase Vision phase detector. As we can see, it is implemented similarly to the other detectors or recognizers, and that's a big benefit to us because that makes MLKit very easy to use. Hi, welcome to barcode scanning. In this section, we're going to discuss implementing barcode scanning on the device and trying out barcode scanning. Implementing barcode scanning on the device. In this video, we're going to discuss working with Firebase Vision Barcode Detector, detecting the camera feed image, and displaying the results on the screen. Looking back to our case switch code, this time we're going to open up barcode detection, and for that we want to look at barcode scanning processor. Once again, barcode scanning processor follows the same structure as all the other detectors, where it implements vision processor base, and this time it returns a list of Firebase Vision barcode. Now let's look at Firebase Vision barcode. The first thing we'll notice here is all the different formats, and these are all different types of barcode formats that can be scanned. So some of the famous ones that we'll be familiar with here is UPC, QR code, ITF, code 39, 93, 128, and by default, of course, it selects all formats, so it just picks up whatever it can find. Now, in our constructor here, as expected, we have a Firebase Vision barcode detector, and we're instantiating it in an expected way here. And we'll notice here in the Google sample code, it gives us this options, but it's commented out. And the note here says, note that if you know which format or barcode your app is dealing with, detection will be faster to specify the supported barcode formats one by one. So that means if we know we're expecting QR codes, then we should put this in because it'll be faster. But if we don't know and we want the app to be able to detect any kind of code or barcode, then we should leave this out and it'll basically pick up whatever barcode we put in front of it. So that's the Firebase Vision barcode detector class. And by now we should be very familiar with detect in image, and that it only does one thing, and that it invokes detect in image with the Firebase Vision image object. And then finally, we'll look at the onSuccess method, which displays the results onto the screen. So from here, we have a list of barcodes, which are actually Firebase Vision barcode objects. And from here, we're going to get each one, and we're going to plug it into barcode graphic. Now let's look at barcode graphic. So barcode graphic, what it does basically is it draws a rectangle around the bounding box of the barcode. And again, there's a very helpful method here. So our barcode here is a Firebase Vision barcode, and it gives us this nice method called getBoundingBox. So again, we don't need to do a bunch of different calculations. And from here, we can just draw rec.left equals translate x rec.left. So it's very straightforward, very simple stuff to draw onto the canvas. And finally, we draw the text where we get barcode.getRawValue. So again, a very simple helper method which extracts the actual numbers of the barcode that we are detecting. And again, these are just the bounds of the text box that we'll be drawing on the canvas. So here we can do a bunch of different things. We can say something like detected and then plus barcode.getRawValue. And again, here you can do anything you want. So one of the things you can do, you can take the raw value here and you can search it. So for example, if you have a database of products, you can set up your application to scan the barcode using MLKit. And then using barcode.getRawValue, you can then get the numbers that were detected, and then you can search that number in your database and retrieve the product or the book or whatever the case may be that your application is using to scan. And that pretty much sums up barcode graphic and barcode scanning processor. Again, it is built and designed in a similar fashion to the other processors. And because of that, we should be able to do a lot of different things with MLKit very easily. Hi, welcome to image labeling. In this section, we're going to discuss implementing image labeling on the device, implementing image labeling on the cloud, configuring image labeling, and trying out image labeling. Implementing image labeling on the device. In this video, we're going to discuss working with Firebase Vision Label Detector, detecting the camera feed image, and displaying the results on the screen. Now, since today we're looking at image labeling, the first place we'll start is on our live preview activity, and we'll go to our create camera source method as we have been in the previous videos and sections, and we'll go down to image label detection. We'll see that our frame processor is image labeling processor. So let's click into that and see what we find. So as expected, we find here that image labeling processor extends vision processor base, and that the generic type that's passed in is a list of Firebase Vision labels. We'll get the Firebase Vision label later, but as you can imagine from the previous sections and videos, that this just contains the data that's found when detecting a label. So it'll likely just contain a string of what it detected. Now the important thing here is, in our constructor, we see the instantiation of detector, and that is a Firebase Vision label detector. So looking into that, this is not a open source class, so we don't really understand what's going on in here, but that's besides the point. We know that for image labeling, we need to use a Firebase Vision label detector. Okay, so moving on down to the rest of the classes here. Again, since this extends vision processor label, we expect that we have a stop method, a detect in image method, an on success, and an on failure. We won't go through on stop and detect an image again because we have been through those in the previous videos, but we know here that it just returns a detector.detect an image, passing in the Firebase Vision image. Now looking at the on success, this is where the results get displayed on the image. So the first thing is it clears the graphic overlay, and then it creates a label graphic, and then it adds it to the graphic overlay. Okay, so let's look at label graphic. So label graphic, as we can see, it extends a graphic, so it's something that's displayed on a graphic overlay. And basically the method that we want to look at here is draw. So in draw, here we just get the X and Y coordinates of the overlay itself, and then we loop through the labels that we got back. So within Firebase Vision Label, again, this is not open source, so we get a bunch of obfuscated variable names. But we can see here from the label that we are drawing a text of label.getLabel. Now, as we can imagine, .getLabel probably returns just the label of what was found. But let's see what else we can find in this method. So if we just do label dot, we'll see get confidence, get entity ID, and get label. So what these are is get confidence is basically when you show an image of a dog, for example, and then the ML kit returns dog or cat, for example, it'll give a confidence level. So it'll say this image is either a cat or a dog, and I am 10% confident that it's a cat, and I'm 90% confident that it's a dog. So within our logic in our code, we can say, for example, only label this if label.getConfidence is greater than 0.9 So then what we're doing here is we're saying only label something on the image feed if we are confident about it. Let's leave this out for now, but we will look at it a little bit later.
There was a development.
Hi, welcome to Landmark Recognition. In this section, we're going to discuss implementing landmark recognition on the cloud, configuration of landmark recognition, and trying out landmark recognition. Implementing landmark recognition on the cloud. In this video, we're going to discuss working with Firebase Vision Cloud Landmark Detector, detecting the camera feed image, and displaying the results on the screen. Going back to Android Studio, the first thing we'll notice in our case switch statement here is that there is no code here for landmark recognition. The last one is image label detection. So, fortunately for us, the processor is actually included in the code. However, it's not included in the demo for some reason. So what we're going to do here is we're just going to go ahead and add it. So after classification, we're going to say landmark recognition, and we'll just type that in here. Okay, and then we need to add it to the spinner as well, so we'll do that here. And then we need to add it to our case switch, so we'll add it to the last one, after the last one. Okay, so we'll call that landmark recognition. We'll say using landmark recognition detector processor, or I guess recognition processor. And then here, we'll need to use the cloud landmark recognition processor. Okay, so now that our UI is all set up, let's go inside and take a deep dive inside cloud landmark recognition processor. So as we see, it extends Vision Processor Base, and the generic type this time is a list of Firebase Vision Cloud Landmark. Let's take a quick look here. We'll see all the obfuscated methods, obfuscated variables, but we'll see that there are 5 public methods here that we can use. So there's getEntityId, getLandmark, which is a string, getBoundingBox, getConfidence, and getLocations. So locations, if we look here, is a list of Firebase Vision lat-long, latitude and longitude, and it just gives you latitude and longitude. So this will give you the list of the possible latitude and longitudes of where this landmark is. The confidence is the probability that they are correct, that this is the landmark that you're actually looking at. So if, for example, you're at the Eiffel Tower and maybe it's a cloudy day or something like that, or there's fog and it can't really be sure, it can say, there's a 0.5 out of 1, so 50% confidence level that this is actually the Eiffel Tower based on the landmark detector. The bounding box is just where the landmark was detected in the camera feed or the image. The landmark is the string, so it's the actual name of what was found. So if you're looking at the Eiffel Tower, this would be Eiffel Tower. And then getEntityId, this would just be the ID of the landmark that was found. Okay. Now that we're past that, we'll look at our Firebase Vision Cloud Landmark Detector, and we'll see that it's instantiated as expected here, getting an instance of Firebase Vision, and then just invoking get Vision Cloud Landmark Detector. We're passing in the options object here, and we'll look at this in the next video. Now, as expected here, getting the camera feed is done just like it is with the other detectors or processors. We're invoking here detector.detectInImage, and we're passing in the Firebase Vision Image object. Finally, in onSuccess, we're displaying the results in our graphic overlay. So here, as usual, we're invoking graphic_overlay.clear, and then we're just adding a log message of the size of the landmarks that was found. So this is just like, let's say it recognized 3 landmarks in the camera feed or in the image. It'll say camera landmark size 3. And then what we do is we loop through the landmarks. And for each one, we get the Firebase Vision Cloud Landmark object. So let's just add some spacing here so it's nice and clear. So there's the clear, there's the log. And let's separate it like that. So we're getting the landmark. And then we're adding a log message saying we found a landmark on the cloud. And if we open up here, we'll see that this is probably the toString, not this one. There should be a toString method somewhere, because here it'll say we're printing the toString of the object. Or we can just say .getLandmark and it'll print nicely. It'll say cloud landmark Eiffel Tower or cloud landmark pyramids, for example. Anyways, moving on. After that, we go into our cloud landmark graphic. So cloud landmark graphic is our graphic object that draws on the overlay. And we want to go to the draw method. And the first thing we do is we do some null checks. So we have to check that our landmark is not null, because it is. We can't draw anything on it. And the second checks we need to do is that it has a name and that it has a bounding box. Otherwise, again, there's nothing for us to display. There could be some other useful information, but these two are key. So the next thing we do is we're going to create a recdef object so that we can draw the bounding box on the canvas. And that's all done here with the left, top, right, bottom. And then we're going to draw the text. Again, here we're invoking landmark.getLandmark, which just gets us the name. So what we're expecting is to have the camera feed and there'll be a box around, let's say, the Eiffel Tower. And at the bottom of it, it'll say Eiffel Tower. And that's pretty much it. Now you might be asking why for landmark recognition, there's only a cloud landmark recognition processor and not a local or a client-based landmark recognition processor. And I haven't been given a clear answer, but I think the reason is just because there are so many landmarks and it requires a lot of different angles and views and conditions in order to process them all properly. So this one really requires the cloud and Google's vast library of ML models in order to get it properly correct.
Oke, baik. Tadi ada yang bilang ya kayak memang masih belum familiar gitu ya mungkin sama codingan yang kayak Android gini. Itu nggak masalah banget ya teman-teman semua. Karena kita yang instruktur pun sebenarnya emang nggak memperdalam juga untuk yang ini. Tapi karena memang untuk kelas machine learning ini harus semua kita jelasin yang menggunakan TensorFlow, dan kebetulan di Android itu memang ada Lite, TensorFlow Lite, jadi kita emang jelasin untuk yang ini. Dan kalau nantinya ini kan bisa juga dipakai karena kita juga codingnya kan masih Lite di Python, dan nanti modelnya yang baru dipakai untuk di Android-nya seperti itu. Jadi emang itu harusnya nanti ke arah Android developer kalau emang untuk code semuanya. Tapi kalau untuk yang tadi, karena aku juga emang akan share codingan Android-nya, jadi mungkin itu bisa buat ditonton dulu aja, buat nambah pengetahuan buat Android-nya. Karena nggak semua emang bisa itu gitu. Kita pun yang instruktur pun juga nggak mungkin expert di semuanya gitu. Jadi nggak apa-apa, cuman buat kita tahu aja caranya kalau mau bikin Android itu machine learning yang dibutuhin tuh apa. Nah, itu kan yang dibutuhin cuman modelnya, model yang udah kita buat, itu yang udah kita save model Lite-nya, nanti itu yang akan dibaca sama si Android-nya, yang akan dipanggil di Android-nya. Terus nanti juga di Android-nya itu yang ditaruhin itu juga di classifier Kotlin-nya ini itu untuk masukin si model yang udah dibuat tadi gitu. Nah, kalau yang tadi TF Lite kita itu adanya di sini nih, di aset convert model TF Lite. Jadi yang hasil Python yang udah kita buat itu masuknya di sini, di TF Lite nih. Seperti itu. Karena yang paling bawah itu nanti kita download modelnya ke TF Lite. Oke, di sini nggak ada. Kayaknya yang pertemuan sebelumnya, yang kemarin itu ada yang sampai kita download bentuk model TF Lite-nya ya. Oke. Kemarin aku sempat coding yang hari Senin itu sampai nyoba buat download modelnya, kayak gitu ya. Ini udah pukul 21.57 dan ini masih ada how to use machine learning in Android app. Ini mungkin bisa nanti ditonton sendiri tentang ini untuk penggunaan machine learning di Android app-nya. Oke, itu slide materi terakhir. Oke, mungkin di sini ada yang mau tanya. Ini nanti aku juga bagi yang iOS juga ya. Mungkin ada yang akhirnya tertarik buat coba lihat yang tentang iOS juga. Jadi nanti aku coba masukin yang iOS sama masukin yang Android gitu ya. Mungkin nanti aku zip filenya biar lebih gampang di-download. Kalau iOS pakai Swift ya. Oke, bentar aku coba cek. Ya, betul pakai Swift. Yang iOS pakai Swift. Nanti aku kasih juga code-nya. Oke, mungkin ada lagi yang mau bertanya. Boleh banget kalau ada yang mau coba terus download Android Studio gitu ya. Kebetulan aku udah lama juga nggak pakai Android Studio. Jadi aku udah uninstall Android Studio-nya, jadi nggak bisa demo buat Android Studio-nya seperti itu. Dan karena yang dilihatin itu hanya lebih ke arah machine learning-nya, jadi cuman penempatannya machine learning itu di mana, seperti itu ya. Iya, kalau pakai Android Studio siapin memori yang cukup. Terus juga RAM-nya ya. RAM-nya juga paling minimal sekarang 8 kali ya untuk jalanin Android Studio. 4 aja itu, RAM 4 itu lumayan, katanya sih lumayan ini ya, lemot gitu ya, radaan kalau RAM-nya 4 jalanin Android Studio. Lama banget. Ya, betul. Android Studio plus step-nya banyak. Seperti itu. Ya, betul. 2022 4 GB itu udah kurang. 8 lah. Sekarang minimal 8 lah kalau mau kayak jalanin Android Studio gitu. Itu pun kayaknya memang kalau tabnya udah banyak juga lumayan lemot ya. Kan nantinya kalau machine learning itu juga bisa kerja kayak bikin aplikasi Android harus ada machine learning-nya. Nah, kayak gini nih nanti lokasi machine learning-nya itu gimana, kita ngerjain apa aja untuk machine learning-nya. Nah, itu kayak gini, kita cuma bikin modelnya, terus modelnya ditaruh di Android-nya kayak gimana. Itu paling nggak kita paham sih. Nggak perlu sampai kita paham bikin Android-nya kayak gimana, tapi paling nggak kita paham cara di Android-nya tuh dipanggilnya di mana, terus habis itu dia masuk kemana, yang dipakai Android itu apanya gitu. Oke, kalau model machine learning-nya di store di Firebase itu bisa nggak? Bisa kok, di Firebase juga bisa. Bahkan kalau mau model machine learning itu ditanamin di cloud, itu di instance, itu juga bisa sebenarnya. Banyak cara sih. Waktu aku ngerjain project yang machine learning buat Android apps itu, aku masukin model machine learning-nya di dalam instance cloud. Jadi Firebase aku juga pakai, tapi cuma buat ini nyimpen gambar-gambarnya aja. Jadi benar biar Android apps-nya itu nggak berat gitu ya. Jadi itu buat simpen gambar-gambarnya itu di store ke Firebase storage waktu itu. Terus model machine learning-nya itu ditaruhin di cloud computing, di instance, ditanamin di instance-nya. Gitu. Mungkin ada lagi. Besok kita udah gak bahas Android kok, jadi besok udah benar-benar machine learning lagi semua, jadi kita cuma bahas Android di 2 hari ini. Oke, mungkin kalau nggak ada, aku izin buat stop share screen. Oke, yang bisa open cam boleh buat open cam ya. Oke, kita mulai dari, oke aku tunggu dulu sampai jam 22.07 deh. Untuk assignment minggu ini kita cuman bikin summary ya, jadi karena materinya kan Android gitu ya, jadi kita nggak minta buat kayak bikin Android juga, jadi cuman bikin summary, nanti aku share detailnya di Google Classroom ya. Oke, aku mulai dari layar pertama. Oke, layar kedua. Oke. Baik, terima kasih buat teman-teman yang udah datang hari ini. Kita akhirin kelas hari ini, kita ketemu lagi besok Jumat, materinya tentang data pipeline. Oke, aku izin buat stop recordingnya.